potential here, and they said, hey, this is some great stuff. And we kind of played matchmaker. I think Don Clark said, he was in a presentation earlier today, and he said we paid for the room. So I guess that makes us, I won't say what that makes us, but we paid for the room. So anyway, they got together, and the whole NFV program, the whole NFV revolution was born. I see Don Clark was in the room earlier now. He's not here now, right? So I can tell the story.
I'll tell you tomorrow, so go ahead.
You'll see him tomorrow, okay. Well, I think he's heard it before, but so when they first started coming out with names for NFV, a bunch of different names were kind of tossed around, and one of them was network virtualization. They just called it that, and it's like, nah, you can't call it that because that refers to overlays. This was a few years ago, so it was kind of before network virtualization had really taken off in a big way. So no, and he said, well, how about NFV, network function virtualization? We went, yeah, that's okay. That's a good idea. So he said, okay, NFV, and that's the name that stuck. So I think we helped to put the F in NFV. So pretty good.
There were two F's actually.
There were a lot of names were tossed around originally, but anyway, NFV is the one that stuck. So that's how we've all grown to know and love it. So what is NFV? So NFV is going from this world where driven by the telcos initially. There's been a lot of other interest as well, but going from a world where we had these dedicated physical appliances, where things were running on dedicated hardware, dedicated ASICs, DSPs, etc. And then, taking advantage of the revolution that we had in the cloud space to take advantage of standard high-volume servers running on a common infrastructure and really allow the virtualization layer to take care of a lot of the issues that to sort of level the playing field, if you will, and virtualize a lot of the specifics of the hardware. And so I'll keep coming back to that in today's talk. I'll show some of the concrete examples of how we're doing that, where we're at today, where we're going. We're doing some of this in our own program, which is Open Network Platform. That's Intel's program. There's OPNFV, which I recently started participating in. I'm on the technical steering committee for that. So we're doing this on a number of fronts. Everything we're doing is really committed to open source. Intel being a silicon provider, we don't see the secret sauce being in the software. Having said that, there's certainly a lot of room for software innovation for people to make money building innovative software. We see Intel providing a lot of building blocks, a lot of the ingredients. If you're familiar with DPDK, actually, that'll help me level set as to, is everyone here familiar with DPDK? Probably a lot of nodding heads. So my understanding is, in terms of the Bay Area, this meeting, next month they're going to have a DPDK deep dive. It was MJ from Intel was going to give that. So I know MJ, he's going to do a great job sort of going into a lot of great detail on that. So we'll talk some of what's in DPDK now, some of the performance we're seeing now, also some of the stuff that's upcoming, but he goes, another whole layer below. So what is Intel doing? A lot of it's around the open source and open standards. You can see the laundry list there. There's a lot of these industry consortiums that we're involved in, that a lot of people in this room are involved in. So we've been contributing to a lot of these, and then what we want to do is take a lot of those ingredients, which are open source, just put them on one platform, one reference platform, so that we could then develop use cases, develop demos, proof points, performance benchmarking, etc., and say, look, here's what you get on this specific hardware, and we can give you the BIOS versions and all that stuff. So you can actually have reproducible, results that you can go to the bank with, right? So that's where we're coming from with Intel ONP. I'll come back a few times in this talk about OPNFV. We started this prior to OPNFV's existence. In fact, a lot of the ingredients that Intel is bringing to OPNFV had their genesis in this program. So in a lot of cases, it's the same people. So it's really our integration efforts that are somewhat independent. They're on slightly different cycles. I'll talk about that. But if we take as an example the work we do in OPNFV around OVS for NFV, that program where we take DPDK, I'll be talking a lot more about that, but that is actually the same people that are doing that for OPNFV are also doing it for this program. I mean, because it's all upstream to the same repository. So it's not like we have a secret repository somewhere that is Intel only code. It's all coming from a lot of the same upstream programs. Okay, so that's ONP, and I'll go into a lot more about what that's about. The next piece is our Intel Network Builders, and this is a program, and you can read all the logos there. Good luck to you. But, when we started, actually, there was probably only a dozen or so, and you actually could read the logos in that slide book. There's 170 now, so I think they just gave up trying to fit logos in there and just kind of like, okay, here's a big blob. Imagine your logos in there. In fact, probably most of the people in this room, their logos are in there. There's 170-something companies in there. So the whole point is to coordinate on, some part of it's marketing program, part of it's, messaging, part of it's, developing white papers and proof points, using our ingredients and using our platform. So that's Intel Network Builders, and trying to build an ecosystem. Because up till now, everything I've been talking about is open source. So, people who make software, they want to make money too. So, there are, for example, people in there who make firewalls, virtual firewalls, and they're showing those and demonstrating those on our platforms. Then, how do we get to the end user? And we start with trials and some initial deployments. So that's where things start to break out. A lot of these ingredients are common across telecom, cloud, and enterprise. As we go forward, I think we're starting to see, we tried to sort of paint this broad brush that, oh yeah, we could all use a lot of the same ingredients. There are differences, and we'll talk about some of those today. Okay. So, what is ONP? ONP is a reference architecture. It is not an end product, so we're not trying to sell you a bunch of software. What we're doing is we're taking these ingredients, we're taking our contributions and everybody else's to OpenStack, Open Daylight, OpenVSwitch. I'll be talking a lot about OpenVSwitch. Obviously, DPDK, KVM, and we're using Fedora currently. I'll talk a bit about that, why we use Fedora instead of some of the others, like OPNFV has CentOS and Ubuntu. But, obviously, if it works with one, it can be made to work with all. We are actually, the next release, going to be supporting CentOS as well. But we're taking all this, and if you're familiar with OPNFV, you'll see some things. It's fair to say, I think, that ONP is both a subset and a superset of OPNFV. And what I mean is, there's some programs that are in OPNFV that we don't have as part of our solution. For example, ONOS would be one. Now, that's not to say that ONOS is a bad solution or that there's anything wrong with ONOS. It's just we had to pick one to optimize on. We've got a lot of developers that are contributing to Open Daylight, so that's the one that we went with. So when we get actually to the specifics of, for example, service function chaining, we're doing a lot around NSH enablement with Open Daylight. So we had to pick one to sort of get out there and be first with. So that's what we're doing. Interestingly, when we started on all this, we actually weren't even on, we started all this before Open Daylight. We started with Floodlight back in the day, that was vSwitch. It was an open source version of vSwitch's controller. And then Open Daylight came out, and a lot of the industry focus went that way, and a lot of our industry ecosystem partners were like, hey, we should all participate in that. We became platinum members, and so we switched over to Open Daylight. One word it's probably worth mentioning on dpdk.org. I don't know how many of you guys are familiar with the way that's structured. dpdk.org is not an Intel site, like it's not, it's actually, it truly is a multi-vendor community now, and maybe it didn't start that way back when. We used to actually initially put the code on 01.org and then it transitioned to dpdk.org. Those days are gone now. DPDK.org is a multi-vendor community. ARM is now contributing. There's some, this actually, a lot, and I'll be talking a bit more about this when we look at where DPDK is going, but there is a lot more multi-vendor aspects to it now. And it is, so don't read DPDK and think, oh, Intel only. All right. So before we get into what we've done specifically on ONP, it's worth going back and looking at the initial goals of Etsy. So why did they want to do this? What were the goals? And the reason I show this is because I'm building, it'll help to rationalize some of the design choices we made. So they wanted, okay, improve CapEx, okay, yeah, everyone says that. But I think making some of these statements actually leads to an architecture and some architectural decisions that you have to go with as you move forward. So this next one is key: flexibility in assigning DNFs to hardware. So how can I take this virtual function and move it from this piece of hardware to that piece of hardware? That will really impact the decisions I make in terms of my virtual interfaces. And we'll get into that. Rapid service innovation, okay, well again, that's having an open ecosystem, open APIs, that all helps to move that along. Helping with the power, that's a lot of the things that actually come along with having the standard high volume servers. And really, keep coming back to this, the standardized and open interfaces. Okay. So, let's go and look at the data plane. So, one of the key elements, the key bottlenecks of this whole infrastructure is people go, well, yeah, but you can't do effective data plane communications on a virtualized infrastructure. So we kind of try to lay out here, here's the challenges. So the first, programmability, and this is where we both mean, having it programmable at a fundamental software layer, but also the control and the policy of it. So if you do have some piece of hardware in there that is, let's say, bypassing a software layer, you've got to make sure that there's that policy control. And I'll show in the next slide kind of what I mean by that. Scalability, this is where, certainly if you look at DPDK, we ported that on things from, the low-end Atom all the way up to our high-end Xeons. Efficiency, performance per watt per dollar. Being able to integrate any acceleration capabilities that might be in the hardware in a seamless way. And you'll see we've got our DPDK AE is how we're trying to achieve that, which will be coming up. And then I think security is another area that, it kind of slices across all the layers. There's a lot to be done there. It starts at the platform level. If you can't secure the platform fundamentally from the BIOS, you kind of, you could have a rootkit. There's a lot that could go wrong there. So it's got to start from that very first initial BIOS step all the way up to runtime. So if we look at different architectures and different architecture options, let's look at, this slide kind of lays out a few of the different options and helps to tell you why we made some of the design decisions we made and why we promote these. It's not to say that other solutions are necessarily wrong, but it's just we need to make these important trade-offs. We've got to look at the performance and the flexibility. So this just lays out, a laundry list of different ways one could implement a virtual function, a virtual network function, A through F, and have a different stack of software running on it. So if we start at the left, what we see is we've got, and I try to use consistent colors across, so we've got a network application that you've written that is running in a VM, a VNF actually, that's running on the kernel stack, going through, let's say, VirtIO, and going to a stock vSwitch. So this is going to be, running, if we start to look at hard numbers, if you're using a stock vSwitch OVS, you're going to be limited by the throughput of that. So that's going to have, if we look at, let's say, 1 million packets per second is probably about where you're going to top out at. Okay, so that's one. Then we say, well, hey, we could get, you listen to us and go, well, I could use DPDK and I could get better performance. Yes, you could, running it in your VNF. However, B, so that's option B, still not a great solution because you're still limited by that hypervisor, so don't do that. Option C is the one that we're promoting and the one that our ONP architecture takes advantage of. You've got DPDK running in the virtual network function as well as in the vSwitch. And it gives you that combination of flexibility, that independence. We're still using VirtIO as the interface point between that VM and the virtual switch. That gives us the flexibility so that we can be doing things like portability. We could run this on any hypervisor. We're using a standard virtual interface. It gives us that independence. We're running it, in our case, an open network platform using OpenVSwitch. If you could run it somewhere else running another vSwitch as long as they support VirtIO, which most do. And I'll talk about the bottlenecks that go through VirtIO as well, and how we've been addressing them. So that's the one that we're doing and that we're recommending for this. There's another option that will give good performance with IV shared mem. So IV shared mem, this is sharing memory between your vSwitch, between your hypervisor domain and the virtual machine. So that gives better performance because you can now, instead of copying the packet, a packet comes in and I go, okay, which VM is this going to? Oh, it's going there, I better copy it, and there's a single copy going that way. With IV shared mem, instead of doing a copy, I can just pass a pointer and go, hey, there's a packet here for you. And so I've got a common pool of memory and I get better performance that way, right? The downside of that approach is now I'm just passing that VM a pointer and it's like, okay, what if he wants to look over here? Well, your security is not there. So we're not recommending that. It's possible, but we're not recommending it. Then, as we keep going right here, I show a couple of SROV possibilities. So what we're losing then, so we're bypassing the vSwitch, so we're getting the best performance we can. I show two options here, E and F. In the one on the rightmost, F, you're going through this stock kernel stack, so it's kind of like, well, why bother getting SROV if you're not going to, if you're now going to be bottlenecked by the kernel stack. Option E, you could argue, yes, good performance, true. However, now I've got that tie, a couple of issues here. One is I've got that pull mode driver running in that virtual function. So with that pull mode driver now, I've tied it to that hardware. So this has a few implications. One is, if I look for, I talk about it as a problem in time and space. If I look at it as, okay, I want to move this, if I want to do live migration, that's an issue. That becomes very difficult to do with this kind of architecture. That's one issue. Another issue, if I look at it in time, I've talked to customers, telcos, large telcos, who shall remain nameless, some of whom may or may not be in this room, and they end up being fairly conservative. And what I mean is, when they have something that works, they keep it. It works, don't touch it. So as an example, there was one that had an application that they used that had a tie to a specific piece of hardware that the hardware company went belly up. That never happens in Silicon Valley, does it? So they could no longer buy this piece of equipment in the retail channel was dried up. They had to go and buy all their spares on sort of eBay and the sort of gray market. So they ended up having a supply problem that they actually kept this application running for, it was over 10 years without being able to get the hardware, and just by buying spares and just hoping that their spares didn't break. So, by having that independence and not having that tie, having a virtual interface, you can get away from some of these hardware dependencies. So it's a little bit different, compared maybe to your, the Google mindset and, some of the people where it's constant innovation, where they're always on the latest kernel version. It is a bit different mindset sometimes. So anyway, just an observation based on real experience. And also the other thing to consider is when I do things like SRMV, I'm bypassing any vSwitch. So now my orchestration layer and any of the policy controls that I want to have in place have to all be there in that NIC. So if, for example, I want to say, hey, I want to implement this ACL rule, well, it's got to be supported in that NIC. So, okay. So this just shows at a high level what our architecture is and what our focus has been. When I drew this slide originally 3 years ago, it was before all the stuff in the green was done by the ETSI. So, it was interesting to sort of map a lot of those upper layers and go, okay, well, we're not doing that in our open network platform. It's interesting that this is the same sort of dotted line, if you will, that OP and NFV made when they started. They said, hey, we're going to focus on the NFVI and the BIP and not touch this other stuff. OP and NFV is starting to wonder if that was the right decision. I think for Intel, this does make sense for us to focus our effort here. The platform is where we have the most value to add, so that's what we'll continue. So yeah, again, we're using OpenStack, OpenDaylight, OpenVSwitch. Sort of those three elements are key. And we just show some examples, whether it be a telco kind of examples or enterprise. So let's look at OpenVSwitch. So we knew that we had DPDK and that we could get some great packet processing numbers and get really, bump up the performance of a vSwitch using DPDK. There are some commercial vSwitches that you can use, you can buy, that are DPDK based. So 6Wind makes one, Wind River makes one, a couple actually. There's some others. So we looked at it and said, well, we think we could do OpenVSwitch with DPDK. So when we started, what we did is we took OpenVSwitch, we forked it, and we rewrote it and said, okay, here it is, we did it all in DPDK. And we did this on OpenVSwitch, I think we started on 1.1. What we quickly found was that was a bad idea. We got great performance, don't get me wrong, but as time went forward, OpenVSwitch went to 1.2, 1.3, and we were behind the times. And we didn't have enough resources to keep up and keep redeveloping features that they did in OpenVSwitch in our fork. So we finally said, no, this is not a good idea. So instead, we took OpenVSwitch, and if you're familiar with OpenVSwitch, there's kind of two paths here, right? There's sort of when you start off, you come in, you go through the NIC, and you go through the standard, the sort of standard kernel module. And what ends up happening is you will cache when you don't know what the path is, you go up to the user space, and it'll figure out where you're supposed to go. That rule then gets pushed down into the kernel module, and that's your path. So there always was this sort of user space portion in kernel space. What we said was, hey, kernel space and user space, well, we do stuff in user space. So let's take OpenVSwitch, and instead of making the user space path the exception, we'll make it the best performant way. And we'll do that using DPDK. So we put in a poll mode driver. The purple bits here are the DPDK portions. We'll make it appear as a net dev to the user space forwarding path. We'll get all our DPDK libraries in there. We've recently added tunnel support in there. So we've got a very good performing solution there using OpenVSwitch with DPDK. And this is available now on openvswitch.org. The problem was, though, then when you looked at the path going to the virtual machine. So what you'll find is that the vhost user, which is sort of the back end, that's the part in the hypervisor, from you got VirtIO up in the virtual machine and vhost down in the hypervisor. That vhost portion was really not optimized. So, for example, to give a hard number, when we first did this, we were able to get millions, going back in time a little bit here, but let's say millions of 5 million packets per second through the vSwitch. But the bottleneck then came in going to the virtual machine. It was about 300,000 packets per second. So, we had a great, a great engine, but we were putting it in a lousy car in the sense, right? I mean, it was bottleneck. So then we started to look at that vhost user piece. We took vhost user, we did our own implementation first. It was another one of these cases where great minds think alike, and the great thing about open source is you have a great idea, somebody else has a great idea, you both do it, and then suddenly you release it and you find, oh, well, you did that too, wow. And unfortunately, there were different implementations. So we had an implementation, it was called vhost queues, C-U-S-E. There was vhost user, so we ended up taking our port and making it all one happy family with vhost user now. So that uses DPDK, and it will now get. I think we immediately bumped it up about 10x immediately, but now we're even better. So we've solved that bottleneck as well. So as we go forward, I'm starting to get to some hard numbers here. Right now, we're at OpenVSwitch 2.4. So there's a couple of slides in here that are just a bunch of text like this that I kind of have to put in for legal reasons. Anytime I show a performance number, I can't just say, hey, we got this, and you go, yeah, well, what was the configuration? So there's a couple of slides like this where I give a lot more detail than you care. Suffice to say, it's a decent Xeon. It's not the highest end Xeon. It's a decent one. It's 14 cores, so there are more cores you can get. So anyway, with this, what we're able to get then, I'm going to give a few sets of numbers. The first one is phi to the vSwitch to the phi. Now this used to be the only number we gave because we got great numbers here. Because of that bottleneck I told you about going to the VM. So this is an interesting number, but it's not, if this is the only number that a vendor tries to show you, then kind of go, well, you might question it a bit. So I just show it for reference. I think this slide is actually useful because it shows, for reference, it shows the 40 gig number there. Just so when we start throwing other numbers out to you, you can go back for reference. So this is coming in on one port, going out another port. Doesn't go to the VM. But still, in terms of the performance, if we look at, so the numbers all generally quote are the 2-core numbers, which is always a design trade-off. How many cores does one want to dedicate to your vSwitch? I showed, on the previous slide, we're on a 14-core Xeon, right? So that's 28 hyper-threaded cores. That's per processor, per socket. So using 2 cores maybe isn't such a bad thing, right? Using 4 cores, you've got to pick your pain point. We think that, we know that going forward that number of available cores goes up. I mean, I know what the number is going to be 4 years from now. I can't tell you in an open forum like this, but if we were under NDA, you could ask. The number goes up. Moore's law, like the number goes up. So, you know, whether you use 2 cores or 4 cores, you know, is that such a big deal in the scheme of things if it gives you the flexibility of all the things we're talking about? I don't think so. That's a design decision that any system architect has to make, but I think it's well worth it. Another point on cores and assigning them to DPDK. In the past, when we assigned a core to DPDK, it was a run completion model, there was pull mode drivers, you were spinning on that core, right? So even if there was no traffic, that core was, you know, are there any packets for them? No, are there now? So it, you know, which is a great way to get performance. However, it does come at a cost of power, which is a real cost. It's not a fake cost, it's a real cost. So what we've been doing in our latest releases is looking at those kind of things and saying, look, we're putting in the control, you know, knobs, if you will, to say, all right, I want to start backing off. If I keep going and saying, hey, is there traffic for me there yet? And there isn't, I want to be able to go, well, let's start backing off and having an algorithm where I can go, hey, I went 3 times and noticed nothing there, then I'll go into a wait state and I'll slow down and I won't have that pull mode driver just always going. So that's sort of the first level of defense is, you know, you can configure it so you will slow down, and if there's no traffic, you won't pull as frequently. Ultimately, and this is in an upcoming release, we will enable an interrupt mode. So if you want, you know, you can set it up that way. It depends on your application, it depends on the configuration you want, you know. Obviously, if you go to an interrupt mode, there's a higher latency, you know, when the packet does come in. So those are the kinds of trade-offs. Okay. Enough of the sort of fake one, which is the fly-to-fly. Let's look at this use case where we're coming in and we've got 2 different 4 ports, and we're going all the way up to the VM and out again. So here, this is and here's what we've done is we've shown it relative to stock OBS. So it's 18 times stock OBS. Yeah, that's for the that's with 2 cores is 18 times. And it's actually about 18 regardless of 64 or 256, which makes sense. I mean, it's not that dependent on the packet size. So we're getting really good performance with that. We're still doing a single lookup here. We're doing 12 tuple lookup. As we look forward to more complex use cases, let's start looking at, well, what if I'm doing something with multiple overlays? I've got something like NSH. You know, what does that start to look like? So in that case, I can have a VXLAN encapsulation, so VXLAN GPE. I've got the NSH forwarding I've got to do. I've got, you know, this is going across multiple servers. So how do, you know, and these, then I have multiple overlays. So I think the need now for a scalable solution with this kind of high performance is even more important than ever. So that's what we're doing. This 1.5 that I'm talking about, we do have VXLAN support. We do not have NSH support yet. NSH will come in our next release. So if we look at that, this again is the tunnel performance, so it's, you know, as you can see, 31 times. And that's doing the VTAP, not NSH, but the VTAP at least. So we will have the NSH in our next, that'll be in the 2.5, which is going to be, oh, and a note on numbering. Right now, we're on, so I'm going to keep all these numbers straight in my head, but right now, the ONP release I'm talking about is our 1.5 release, which uses OpenVSwitch 2.4. We're changing our number. We figured we had enough changes going forward, so we're changing to ONP 2.0 is going to be our next release. So that's what's going to come out in January, or sorry, at the end of this year. The end of this year will be our ONP 2.0 release. So that will then be tied to the next release of OpenVSwitch. This is where you get into, and you know, looking at OP and FE. we have this discussion all the time in ONP. It's happening right now in OP&FV of, well, if I've got, let's say, Open Daylight and NSH support is in Beryllium, but I know Beryllium isn't quite out yet, but I have the NSH in my vSwitch and I want to be able to demonstrate, so we kind of have we always get ourselves in this quandary. Fortunately for our ONP program, we've been on a quarterly cadence, so it's not quite as bad. So if we miss it, then it goes, the next 3 months out. We have had this discussion around OP&FV, and their cadence is still a little bit, about the 6 months, a little bit more. So it's even more of an issue sometimes, but it's always a challenge, and everyone's got to make their decision. What's more important, getting the feature in or having everything already upstream. So we all face the same issues. I think it's fair to say in the case of our ONP, we try to err on the side of trying to at least have all the ingredients, and I'll show what I mean by that with the service function chaining. There's things happening in OpenStack, there's things happening in Open Daylight, there's things happening in OpenVSwitch, all of which have to work together to enable some complicated feature like service function chaining. So we'd rather err on the side of, hey, here's a patch to Lithium for Open Daylight than, say, well, just wait. So that's always a trade-off. Yeah, there's just some more details of the system setup. Okay. So far, I've just been talking about the virtual interface and the vSwitch and all that. If we look at, there's a lot more to a data plane than just the vSwitch and the network interface. We look at things like the crypto devices. We look at things like DPI. Look at things like where we can do classification in a NIC. All these things we want to be able to expose to the software, to the system software, in a way that isn't tied to that specific hardware. So that the easiest way to understand this is to look at crypto, because I think we can all kind of understand crypto fairly easily, even if we don't understand all the algorithms. But let's say you want to encrypt this packet. You could either use AES-NI, which is a standard feature of these Xenons, and do it in software. Or if you had an offload device, you could say, okay, do it in the offload device. The decision on whether it's better to do it in software or offload to hardware will depend on the size of the packet. Honestly, if it's a 64-byte packet, you may as well just do it in software using AES-NI. If it's a big packet, you're probably, if it's, 1K, 1.5K, you're probably better off in hardware. So this is where we're putting in these APIs and want to put that decision, and that decision point will always move depending on the specifics of your hardware. So we want to have these APIs where you say, encrypt the packet, and you figure it out, right? So that's the kind of thing we're doing. This is also a good time to talk about third-party support. So you'll see in here this QAT in the picture. That's our quick assist technology. That's an Intel specific. It's part of a chipset that we developed. I was one of the architects on it. We also sell it as an add-in card, so it can do, right now, it'll do 40 gig of crypto. So it's a good offload solution. There are others out there, competitors, some of the ARM community as an example. So what we're doing, and this is why something like OP&FV is so important. We've been working with the ARM community to try to come up with APIs and a way of working with them so that it can all work together. So that and that's where this thing in there that says simple stock model. We want to be able to enable third parties, whether that be an ARM solution or what have you, that could sort of offload some of these in addition, instead of, if you don't have quick assist, so that way, again, that decision point you know, of whether it's better to offload or to do it in the software will always be there. I mean, that's sort of a fundamental, you know, architectural decision. Just because software, it can be operating out of the cache. If you're offloading it in hardware, well, it's got to go PCI buses to traverse and whatnot. So there are different considerations there, but that's where we think doing things through a common API makes sense. So I won't belabor the point, but that's kind of where we're going. All the stuff on the left of this diagram, that's sort of our stock DPDK APIs and functions. You know, if you kind of went through all the details in there, we support all our standard Intel NICs. We support some Mellanox, and we support the Cisco VIC, and you know, there's a variety of different full mode drivers out there. And it is an open source community, so if somebody came up with a new one, that they could add a full mode driver for their device. Okay, enough on that. So next, I'm going to talk about OpenStack, and so shifting gears a little bit here. We've been contributing. We're actually, let's see, I never saw the numbers for the latest release for Liberty. On Kilo, we were in the top 10, so in terms of contributors to OpenStack. We contributed across a lot of vectors here. You know, I'm representing the Network Platforms group that's who pays my salary. So, you know, the areas that we primarily contribute to have been all related to packet processing and NFV. So, for example, in Neutron, if you set up the DPDK-based vSwitch, we want to be able to identify that as a port type and be able to take advantage of that. So that's just one example. There's some enabling, and you have to make sure that DPDK is enabled on platform. So there's some glue logic there and some work we had to do to enable all that. So a lot of the work we did in OpenStack and OpenDaylight, at least initially, was related to that. That was sort of job one. Looking at the broader Intel, there's a lot of work that we put into across a variety of vectors, one of which is security. So trusted compute pools. Trusted compute pools is a way of ensuring that the platform has booted to a known good state, and if I have a workload that needs to be run securely, it will only go on a known good platform. That's one example. They're continuing to build upon this capability, so that would be another whole hour presentation in and of itself, or longer. I won't belabor all the other points on this, but I think I did want to touch on this one. Enhanced platform awareness is an umbrella term we've used to signify, you know, what is it that the orchestrator, that the BIM needs to know about the platform. So one of the issues is that OpenStack, a lot of these capabilities came about because, you know, from the cloud space, and where you just looked upon all your sea of compute platforms as all homogeneous, and it didn't matter exactly where things went. Every platform was the same. When we start to do some of these optimizations that I've been talking about, like using DPDK, it ends up, well, it does matter. This is not just everything going through the kernel and the bottlenecks or elsewhere. We could introduce new bottlenecks by bad placement decisions. So that's just what this is talking about, and it's based on some work we did with Telefonica. So, you know, you could get significantly reduced throughput and a lot of unpredictability in terms of your latency, etc. So what we've done then is looking at, and this was in Kilo, when you want to do your workload placement, you can say, okay, this is where I might be putting things initially. However, I've got to make sure that my memory lines up, and then what I can do is I can go, okay, we have this NUMA awareness piece, right? So with NUMA, non-uniform memory access, right? it allows your memory to look, the same, whether it's on socket 1 or socket 0, but then it does matter in terms of the latency to the memory. So that's one aspect. Another aspect is the NIC. So if you're running that pull mode driver and you are running it on the other core, the other socket, it's got to cross that internal bus to get there. So that's not great. So those are the kinds of things we've already had those in place for a little while now. So looking ahead and kind of where we're going with a lot of these things, there's a lot more we want to do. Some of these we've already got in place. Some of them, like the cache allocation technology, will start at the bottom there. So that's CAT. Cache allocation is a way to say, okay, I've got this set of 10 VMs running on this platform. I want to have some sort of policy that says everybody gets their fair share. Or maybe I don't. I want to say, well, these 3 VMs are special. They get their VNFs that are doing firewalls, and I want to treat them special compared to these other 7 that are doing application work that, maybe it's not as time critical. So that's the kind of thing that we're working on right now. Okay. As far as the controller goes, I already mentioned that we did a lot of work around enabling our DPDK vSwitch, so that's already in place. We've also put a lot of effort into making, there's been a lot of issues between Neutron and Open Daylight. We've been part of the community supporting the fixing of that. When we started, we actually had a very small team initially on Open Daylight. We ramped significantly in the past year. And we've done a lot of bug fixes, and that's always a good way to get to learn the code and to contribute to a community when you're starting. So we've done a lot of that. Where we put most of our efforts in the last short while has been around service function chaining. So the service function chaining is a really interesting use case because there's so many moving pieces here. We've put in, we've got patches to OpenVSwitch. They've been submitted to openvswitch.org. They're arguing over the details now. They haven't been accepted, but it's on the mailing list. So we've got a service function forwarder. So I set that in the picture. We've got a classifier. Again, these are rules that get pushed down to the vSwitch to implement these functionalities. So I could spend 2 hours. I have given a 2-hour class just on service function chaining, so I won't do that here. But the service function forwarder is, okay, looking at the NSH header and saying, well, where does this thing go? The classifier is when things come into a service function chain and you don't know, you haven't yet figured out the NSH header. So that's the thing that actually puts the first NSH header and sort of sets up the path. Which services need to be put in place. That's kind of the 2-second version. In Open Daylight, we've contributed significantly to the service function chaining code there. There's a lot of work ongoing in OpenStack. As an example, Tacker. These are the kinds of things you don't realize till you actually start doing and trying to implement. When we first instantiated a service function chain, there wasn't any way to tell, like, hey, okay, I created this VM. Let's take it as a firewall. Everyone understands the firewall as a use case. But what if it hasn't been provisioned yet? I can't actually send any traffic to this thing until it's been provisioned. So that's where you need this higher layer awareness, and we're using Tacker for that function, to say, okay, this firewall has been provisioned, so now we can start accepting traffic. We can make it part of a functioning service chain. So that's an example. There's a lot more complexity to it. And a lot of these pieces are still moving. It's an active area of development. So. All right. So that was it for Open Daylight. I'm coming to the end of my talk here, so I'll get specific on what do we deliver in our ONP. In 1.5, it's out there. So we've got a bunch of documents. So these documents, the sort of typical release notes, app notes, but also the architecture guide. We've got links to scripts that build this whole thing. Now, obviously, it's running on Intel servers. Actually, I shouldn't say obviously Intel servers. We actually run on some of our microservers too, but it's obviously Intel products. That's what we, somebody could have modified the scripts to run on something else, but. So each release, we kind of look at which use cases we're trying to target and which platforms we want to target. This release we're talking about now, 1.5, was on our as well. It actually was that one I gave the reference. We did it on the 14 core and the 18 core. A previous one we did on Rangeley, which is an Atom. So that's I think we did the 4 core and the 8 core. We're going to do the Broadwell DE. That's the system on a chip that recently came out. When Broadwell EP comes out next year, we'll support that. So there will always be a latest and greatest platform, and there will always be sort of good, better, best. You'll have the Atoms, you'll have the SOCs, you'll have the standard high volume Xeons. We tend not to choose the highest end SKUs of the Xeons because those aren't as common, but we choose ones that are sort of in wide use. So this gives a list of everything there that we, in terms of the versions, if you care, Kilo, Lithium, SR1, etc. You might ask, well, Liberty's out. Why didn't you use Liberty? Well, again, it's a chicken and egg. There's all these moving pieces. We have to have time to integrate and test, validate, etc. So, which is the same thing that, of course, OP NFV goes through. So this is my last slide. So just want to drive home a few key points here. So we are fully open source. Nothing we do is secret sauce in this. Everything's aligned with all those open source major upstream projects. We are doing things quarterly, so that gives us a bit quicker turnaround on some things, especially those things with a lot of moving parts. We're always going to optimize for the latest Intel platforms, and won't apologize for that fact. Those benchmarks, I didn't spend much time on that one. The graphs I showed in there, they were from the benchmark reports. It's an 80-page document. I mean, this is not just with text and the whole bit. So it's a lot more than you want to know, but it allows you to reproduce results. As far as OP NFV goes, we're a subset in many respects because we don't include, OP NFV has right now 40 projects or so, a little bit more. So some of them we don't include. Some of them we will include in the future. For example, vSperf did not come. I mentioned OpenVSwitch was one that we developed. vSperf, even though Intel was actively involved, was driven through OP NFV. DPAC is driven through OP NFV. We'll bring those into ONP at the right time, which is real soon.